is going to be the lecture number 13 on the week number 8. Okay, today I'm going to start to talk in the chapter 5. We are going to talking about the approximate analysis of statically indeterminate structure. The approximate analysis will be different from what we have learned before. Before that, the method, we call it the exact analysis, based upon some assumption that we have made. For example, under the application of the force, the behavior of material is linear elastic, and also the deformation of the structure going to be very small. Based upon what? Based upon the free body diagram, based upon the equation of equilibrium, and based upon the compatibility equation, based on the force displacement relationship. In the analysis of statically indeterminate, we classify the method of analyzing into force method. Another one we call it the displacement method. Okay, displacement method. The force method we study in the theory of structure, such as the consistent deformation, in which we use what? We use the redundant as the unknown. We saw the unknown to determine the force and the moment that we are looking for. And by the force method, we are looking for the degree of indeterminacy of the structure. For example, if we have the frame like this one that we have from the examination, and the frame subjected to the wind load. In this case, we apply the lateral load. And then this frame has the degree of indeterminacy of what? The reaction going to be 3 plus 3, that is 6. We have 3 equations of equilibrium for one free body diagram. So the degree of indeterminacy of this frame going to be 3. So we got to select 3 redundant to so forth. And another method, we use the displacement method, such as what? Such as the slope deflection. The method going to use what? In the slope deflection, we use the slope and we use the deflection as the unknown. Based on this one, we consider what? We consider the degree of freedom under the application of this force. The frame will deform roughly about this. The frame has the rigid joint. When the frame has the rigid joint, the angle, the normal angle of the beam and the column will keep at the same normal angle, and then the frame defect. And based upon this so-called the elastic curve. From the elastic curve, we can see this frame will has the side sway. It's going to be the delta, and the delta over here and delta over here, they are equal because there is no axial deformation of the beam and the column. And also over here, you have, let's say this is theta B, this is theta C, they are equal. And the theta, this delta, the theta sub B over here and theta sub C over here will add to be 3 unknown degree of freedom. And then you can solve for this unknown, and then you can determine the shear diagram and the moment diagram of the frame. That's what we call the exact analysis. Based upon what so-called approximate analysis, we going to convert this frame into the frame that can be analyzed by using only the free body diagram and can be analyzed only for the equation of equilibrium. That means we support to add more what? More condition, more assumption into this way. Under the application of this force and based upon the elastic curve, you can notice that we have the inflection point occur approximately at the middle of the leg of the girdle and at the middle of the height of the column. What is important for the inflection point? The inflection point is the point that has the moment equal to 0. So based on adding 3 more summation of the moment equal to 0, we can analyze this frame based on the approximate analysis. So the main concept of the approximate analysis is you are going to check is changing the structure from the statically indeterminate to be the statically determinate. Can be solved by the free body diagram and equation of the view. That is the main concept of this method. Okay, anyone who won't understand this, stop my video and watch it again and again. Under this approximate analysis, we will consider the lateral load. This is the example of lateral load, such as the wind load. And we also consider the structure under the vertical load, which is going to be the dead load and the life load. The dead load may be the cell weight of the structure. The life load may be the function of the structure, such as if you design the structure for the university, the building for the university, you got to use at least 300 kilogram force per square meter in the design of the building for the university. But if you design for the building for the kindergarten, you may use at least 150 kilogram force per square meter. That is going to be the original the origin of the analysis, no matter is the exact analysis or no matter approximate analysis. You got to determine the loads carefully. Okay, if the loads are wrong, your analysis will be wrong, your design will be wrong. And again, I suppose to mention it, the load, dead load and life load must be follow the building code, okay, not follow the design code. The design code you use, the design codes that you use is not legal, but is technical. This one will be used for such as the what's so called the load combination. For example, dead load books life load, or dead load books life load books wind load, those kind of things. And then after you can determine the load correctly, you will analyze the structure correctly, and then you will decide the structure, get a good result of that. And next, you must analyze the frame, usually by using the approximate analysis. Again, the frame in this consideration will subject it to the vertical load and will subject it to the lateral load. So we will start by considering the frame subjected to the vertical load, and later we will consider the frame that's subjected to the lateral load. What is the lateral load? Again, over here, such as the wind load. Okay, that is an example of the lateral load or the earthquake loads. And for the this chapter we have two homework. Okay, I remember 1.2 supposed to be the vertical load, and 5.3 is supposed to be in the lateral frame. Frame is a kind of a structure. It's fabricated by integrating, connecting the beam to the column. For example, over here, this frame is the steel frame. Over here, the right one, this frame is the reinforced concrete frame. Most of the reinforced concrete frame, due to the construction of the structure, the joints of this reinforced concrete between the column and the beam, most of them are rigid joints. Okay. However, when you consider the steel structure, some may connect by rigid joint, some may connected by the pin joint. So the thing that also very important for engineer is how we model the structure. Okay, you may model the structure. For example, you model the support as the fixed support, the pin support, and the lower support. But for this one, for sure, you're supposed to model the frame, the reinforced concrete frame, to be the fixed support. Okay, and the joints also be assumed to be the rigid joint. So the beams are connected, and therefore most of the frame are statically indeterminate. So the analysis of the frame usually very complicated, and then we can perform it easily by using a computer program. But after I listened to the comment from the of the committee in the improvement of our international program, one of the comments that a professor said, we got to teach our students to be able to use the hand calculation first before they use the computer. I asked him why, because he said, if you cannot do it by hand, how can you do it by using the computer? Since when you put the the wrong information into the computer program will generate the junk to you also. And then you got to use your experience. You got to use your EMC experience. You got to use your skill to check, okay, the correctness of your computer program. That's why he said we got to understand, we got to be very skillful in the manual analysis. Okay, at this point, the analysis of frame can also be separated into the exact analysis and the approximate analysis. And then if you get some example, you may use your skill to analyze the structure. For example, this steel frame is the rigid steel frame. Is a small building near my house. This frame has the support in the form like this. So how the engineer going to model or going to analyze this support? And as you may see, this support is a kind of fixed support. Okay, the end of the column has what so-called here is the stiffener to stiffen the support, and there is some bolt attached this end of the column, this plate bearing into the support. Okay, that means you got to make some assumption when you like to analyze the frame. Most of the frame that we study has this kind of model. And then you consider a little bit further, there are connections between the frame and this column. We call this is the rigid joints, okay? And that means when you model the structure, you may put some symbol to make it as the rigid joint. And you can see this is not the end of our modeling. There are another beam on top of this one, okay? So you got to put the second layer of the structure, and this one go to by the same column, and it has what? It has a cantilever portion on the left and on the right to take care of the roof, okay, in order to provide the shape to this structure. And also, if you take a look on the left hand side, there is another cantilever out to take care of the cover, okay, of the structure. This cantilever take care of the portion of the roof. And then, like I said, after you do the model of structure, you got to determine what the load is going to apply to this frame. So you got to go to the building code. Anyway, if you consider this structure, there is the purlin, okay? The purlin take care of the weight of the structure, and then the purlin gonna transfer the force acting upon this one, okay, at the end of this one, and this one, and this one, and this one, and this one. So it's your duty to imagine how the load applies to the structure. This load transfer from the roof to the small purlin to the beam and transfer to the girder of the beam. And then at the end of this, there is also a point load applied here. And not enough from that, the beam here also have its own weight. So you got to put the uniformly distributed load all across of the length of the beam on the bottom beam and on the top of the beam. Okay, now you get the model, you get the load, and you can see this structure gonna be statically indeterminate structure. And for the analysis of this, you may see you have 3 for the fixed support, 3 for the fixed support, 3 for the force and moment internal of the beam. So you have the total of 12 unknown. And then you can separate this frame into 2 portions. So you're going to have 3 equations time to free body diagram. So this structure gonna have the total of 6 degrees of indeterminacy. That means you're going to propose 6 redundant to solve this frame. Is going to be very tough job to do so. And then we analyze it by using the displacement method? Yep, you can solve it by the displacement method, but you will consider under the application of this force, you may have the sideway on the second floor, and you have the sideway on the third floor. You may have the slope at each joint 1, 2, 3, 4. Theta 1, theta 2, theta 3, and theta 4. And then you're going to solve for 5, at least 5 degrees of freedom. Now, if you would have the computer, the analysis that solve for this kind of unknown going to be very tough job. So there is a purpose for very senior engineer, how we simplify this type of structure that can be solved by using the free body diagram and by using the equation of equilibrium. Okay, and anyway, for the typical work in the typical office. You also have the computer program to model the frame in the 3D. But anyway, let me say again, it maybe feel very convenient to have the computer program to do analysis of this kind of structure. However, let me spell it. If you put the, let's call the incorrect data into the program computer, this program, this incorrect data will provide you with the incorrect result, and then you must be really careful when you use the computer program. One of the best practice to develop your skill, to develop your experience, to use, to check the result from the computer program. So, like the professor said, since you are the young engineer, it's better to start by working with your hand calculation. Anyway, if you consider this frame, most of the frame in 3 dimensions, if you use the manual calculation anyway, you got to model this structure. And then if you model it in this direction, you will get the frame like this. But if you model this structure in this direction, your frame is going to be more complicated. Now, your frame can be modeled into dimension like this. And again, if you check for the degree of indeterminacy, this one will have 9 unknown, 3, 3, 3. Okay, and then you have only 3 equations from one free body diagram. So this one going to have 6 degrees of indeterminacy. It's going to be a tough job. Okay, if you do the manual calculation. But for the approximate analysis, we will make some assumption and make this analysis of this structure going to be simple. And let me tell you again, we need to consider the frame that not only subjected to what's so-called the vertical load. This is called the vertical load. Vertical load are from what? From gravity of the earth. Okay, and we also have the lateral load. And let me tell you again, this lateral load mostly come from the wind load, because the earthquake load in Thailand is kind of rare. Only some area we supposed to consider the earthquake load. Okay, let me conclude that there are the computer program, even the 3-dimensional computer program, and again, incorrect data will be provide the incorrect result from the computer program. You need skill and experience before you can use the computer program correctly. And there are a lot of structures that are complicated. They are complicated more than we can do the frame analysis. But let me tell you, in the past, the experiences engineer. Most of the time, the experienced engineer in the plant, when they work on this kind of complex structural system, they consider the structure into pieces. For example, they consider the floor. They didn't model it in 3 dimensions, but they consider the floor of the structure. It can be one way or it can be 2-way slab. Okay, and then they use the one-way load distribution, 2-way load distribution to analyze the floor or the slab, and then decide them. And then after they finish decide the form. They work again to transferring the load from the floor to the beams. Okay, the beams may be considered only a single span beam. Okay, the beam also can be like the continuous beam. It depends on how the structural system connect to each other. Okay, if it is a principal beam, you may use only engineering statics to solve it. But if the beam is like this, it's going to be statically indeterminate beam. But anyway, in the design of the structure, for example, for the reinforced concrete design, there is the design code. Okay, there is the design code such as the ASCI design code that provide you how to analyze the structure. And also the ACI code also provide you the moment coefficient for some cases for you to use, and I will mention this later. And then after that, the structure, okay, will be transfer the load from the floor to the beam, and then they transfer the load to the column. And most of the time they assume the column as the short column, okay, and then all the load will transfer to the short column as the what? As the compressive forces, okay, and you design the column unit. And then finally, if you do it from the roof to the fourth floor, third floor, second floor, first floor, until the end of it, you transfer the load to the footing or to the foundation of the structure. This kind of work have been done from the old days and used it for many years, and it has been proven from the past that this kind of method of analysis and design is usable before the computer come. Okay, and then for nowadays you got to use the computer also. You are the new version of engineer, not only working by this kind of manual structural analysis and design, you got to do the computer structural analysis and design. There are a number of programs that you may use. For example, you may use the ETAP, you may use SAP 2000, and there are a number of programs. And again, the professor said there are a number of computer programs. When the companies just change the program, if the young engineer has not so good basic knowledge, they're going to have the problem, because the way to use the program computer is depend on the program. Okay, each program has their own way of application and have their own way of analysis procedure. But no matter the computer program change, the concept of the structural analysis still be the same. That's why he said, not only manual calculation, the concept of structural analysis also will be very important. The young engineer also must understand the assumption, the limitation of the tools they are using. Okay, so this kind of thing I would like to tell you, and you're supposed to classify how you should use and how you should work. But computer program is a must, but it's not that necessary. The concept of structural analysis, the assumption, the limitation, always important, because no matter you change the program, all of the things still the same. And then based upon this, it requires you to develop the skill and also called the knowledge. We call this knowledge, which is required to develop your skill and also your aptitude to be a good engineer. And based on the skill and aptitude, you are going to be the experienced engineer, and you may get the salary 200,000 baht or 300,000 baht if you are very good one, if you can work on the structure that no one can work. Next, I show this picture to you since this one is in front of the student activities building. It just finished a years ago. This is also a beautiful frame. We call this one in the form of cable frame. Okay, I didn't mention much about the cable frame because when you analyze the cable frame, the beam and the column will be framed into the structure like this. So the structure like this will be a little bit harder to analyze compared to our typical rigid frame that we have studied before. But it is your duty. Okay, most of the time I show you the frame in the form like this. But I like to show you in the form like this. Also, there are many uses in the foreign country. For example, for the airplane cargo or the airplane parking garage in the US, a number of them have this kind of shape of the frame. And this one also show you in the front of the student activities building is very beautiful. Again, the cable frame can be classified as a type of our rigid frame. And the frame going to be what have this type of frame has the degree of indeterminacy equal to 6 minus 3. That is going to be 3 degrees of indeterminacy. Okay, this is a good one. And then to be able to work for the analysis and design of the structure, let me show you this one. This conway, okay, built by using a steel column connected to the steel beam, okay, with the rigid connection at this one. And then you can see, you can go to the student activities building and take a look at this one. And let's say this is going to be the rigid joint, rigid joint. And under here, this is going to be fixed support. But if you consider this frame is going to be the statically determinate frame, in which you can use the free body diagram and you can use the equation of equilibrium to solve it. Okay, the cable frame is over here. See, I took the picture here. And before you can analyze and decide, you must transfer the force from the loop to what? To this beam, to this beam, and to this beam. And not only the load transfer from the loop, you also have the weight of the beam, which is going to be the statically, going to be the uniformly distributed. And I like your guy to do some practice. You give the dimension. You may analyze this frame to determine the reactions, okay, at the support, and you study the soil mechanics. You can be design the footing, or you can be design the foundation of this frame. And also you may use the knowledge from the theory of structure. And then you may what? You may draw the shear diagram you may draw the moment diagram, and you also can draw the elastic curve of this frame. This one is supposed to be very easy for you guys, but when you do this one, you get the result of the Mmax, you get the result of the Vmax. So in the design, from the mechanics of material, you will set sigma allowed equal to M and time Y divided by the moment of inertia, and this is going to be the maximum moment from the moment diagram. So you determine I over Y. Okay, I over Y is going to be M max divided by sigma allowed. What we are going to determine is going to determine the size of the section, okay, of this frame. How is going to be width, how is going to be depth, how the thickness of this frame going to be. Okay, for the statically determinate frame, you can analyze the structure based upon what you have learned. But when the structure is statically indeterminate like this, you cannot analyze the structure directly. You got to make some assumption. For example, you make assumption this one have the moment of inertia of 2I, this one going to be I, this one going to be I. So the moment of inertia is going to be the thing that we require to use to determine the analyze for the force and moment in this. If you go back to the slope deflection and you like to determine the moment M sub AB, is require you to use 2EI over L and then have 2 theta A plus theta B minus 3 delta over L or 6 and then plus fixed end moment AB. And you can see from this equation, you guys must at least, okay, know the relationship between the stiffness of each member. And this is the main unknown that we don't know. Then in the analysis of this one, okay, for example, analysis of this frame, you require to know the actual moment of inertia before you can get the exact analysis result. Okay, Ajahn, how about this problem? This problem you can analyze it and you will get the exact result. Okay, most of the time for the design of structure, we don't know the size of the structure. We don't know the eye. Okay, but for this one, you may do the analysis, but you analyze this structure to find its stiffness, its thick, and its stiffness under loads. Okay, but actually you don't have much authority just to find it can resist the load by setting the stiffness enough or not. Okay, this means you check what's so-called adequacy, adequacy of the structure. Okay, it's not analyzed for the design. So in the early step, it analyzed for the design. It's not analyzed for the adequacy of the structure. This is like for the design. You got to what? You need to find the eye. And when you talking about this, you may have many ways. Okay, you may look at or investigate the O and similar structure. For example, if you're looking for, if you are designing for the commercial building, and that is going to be 4 meter No, sorry, maybe have 5-meter span, and you have another 4 span in depth. Okay, for example, if you're going to design the structure that have 5 meter, 5 meter, 5 meter, and 4 length of this one. Okay, and then you have the structure that's going to look like this, and maybe the height is 4 meters. You may just go to some building that's similar to this, and you go to measure the size, and the size of the beam. Let's say the dimension of the beam and the column to be used as the guideline to determine the moment of inertia. Okay, but if you you have a lot of experience, okay, you may use your experience to estimate the size of the beam and the size of the column. Okay, that also can help. Okay, you may look at the old building, or you have experience, you can estimate the size of that by yourself. Okay, how do engineers do to get the eye? That is as close as the final actual eye, where you in the early step of structural analysis. So I give you 2 examples. Okay, to do so, you may do the estimation. Okay, you can go to check for the old building. So typically in the design procedure of statically indeterminate structure, the first step, okay, is require you to do carefully, because it's going to require you to follow the building code, okay, to follow the design code. You got to understand how to find the load acting on the structure, okay, find the load. And then after you finding the load, you got to determine the degree of indeterminacy of the structure to know how you supposed to set up the condition in which you change the statically indeterminate structure to be the statically determinate. Okay, I will tell you later. And then you got to do the approximate analysis. Okay, you are going to study in this chapter. And then you do the preliminary design in order you to obtain the moment of inertia, obtain the cross-sectional area of the structure. And again, I tell you, you can do this by 2 ways without doing the approximate analysis. You may use your own experience. Okay, you may also use to investigate the old building. But if the structure you are designing is not the structure typically seen in the real world, so sometimes you may require to do the approximate analysis to get the moment of inertia, the estimated moment of inertia. Then you use that I and A in the step number 3 to do the structural analysis to get the more exact solution, and then your design going to be close to the real thing. You do redesign the structure. So as I said, in the step 2 and step 3, you may use the experience, or you may observe for similar structure. So the benefit of approximate analysis, first, is going to help you, assist you in the design of statically indeterminate. It also enhances your engineering comprehension on the structural behavior. You got to use in the approximate analysis. You got to see how the structure deform. What is going to be the elastic curve of the structure? And if you going to consider the elastic curve of structure, you got to understand how the structure are supported, and you also got to write to draw a correct moment diagram in order you to estimate or draft a good, correct, elastic curve. Okay, that's require you to get a more comprehension on the structural behavior. And then it also can be used to cross-check the result from the method of structural analysis. Also, the result from the computer program. Okay, it has some guideline to work on this. Now, let me say again, the frame we are working here will be subjected to type of loading. One is going to be the vertical load, okay, and then I say again, the vertical load going to be the dead load and live load most of the time due to the cell weight of the structure, due to the function of the structure. It may be used for the storage of the materials. It may be used as the building in the university. It may be used as the building for the kindergarten. So that's going to require you to find a live load again for what's so-called the building code. Okay, this is going to be about the law that you got to follow. Now, most of the rigid frame has the very high degree of indeterminacy. How do you define the degree of indeterminacy of this frame? Okay, again, it's very easy. This is fixed, right? It's going to be 3, 3, 3, 3. Okay, that is going to be the reaction. And then you got to cut, okay, the internal beam. And each cut of the internal member, you're going to get the moment, you're going to get the shear, and you're going to get the normal force. There are 3 of them to be the unknown. So if you follow this, your degree of indeterminacy will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to be 30 unknown. And then by cutting the structure, and get the unknown, you separate this frame into 4 free body diagram. 1 is here, 2 is here, and you have this one for 3, and you have another one for 4. So the number of equation of equilibrium that you have is going to be 3 times 4, and the degree of indeterminacy of this one going to be 18. And then can I just do like this? 1, 2, 3, 4, 5, 6. 6 times 3 is 18. Yes, you can do so. But if your frame has the pin support like this, you cannot only count as I previously lectured. Okay, if the structure has the pin support, the degree of indeterminacy here gonna be only 14. Okay, and then how come that is going to be 1, 2, 3, 4, 5, 6? Okay, and then it's 6 plus 8 because the pin has only 2. Okay, 2 unknown. So you have how many of this? You have 26. And then you cut it again, cut it again. You have 4 degree of 4 free body diagram. You have 12 of equation. So this one is going to be 14. And then if I can conclude this one. So based upon this, I just reduce the number of the unknown reaction from this to 4, and then 18 will change to the 14. That is right. Yes, that is right. And based upon this, you guys can be estimate the degree of indeterminacy of this frame easily. And I will let you guys do by your own how many degree of indeterminacy of this frame is. Okay, and then in 18 degree of indeterminacy, and if the support had changed from the fixed to the pin, the degree of indeterminacy reduced from 18 to 14. Now, the concept of approximate analysis. The concept is going to be very easy. We will reduce the statically indeterminate structure into the structure that can be solved, which is going to be statically determinate by adding the observed structural behavior in the analysis. For example, you put this inflection point into this frame, and then based upon this, you can separate this frame into two portions. Okay, and then based upon this, you have, for example, the load here for 10 kilonewton, and you assume this one to be, not assume, measure this one to be 2 meters and 2 meters, and you assume the inflection point occur here 2 meters from the fixed. Okay, you can prove this one very easy. Okay, you may fix this one here, and then putting the load here, your elastic curve going to be like this, and then the point about here, is going to be the inflection point. And based upon this, you can estimate the force that occur over here. Even though this is going to be the pin, but due to the beam, summation of x sub x equal to 0. This a sub x is mostly 0, and also the force over here gonna be 0. And since this one is the inflection point, what important? The moment here is going to be 0. So you can take the moment here to be 0, and you can determine a sub y times 4 equal to 10 times 2. 10 times 2 is 20 divided by 4. This is going to be 5 kilonewton. Summation of the moment about B. B is here. A is here. C is here. Okay, about point B. A sub y times 4 equal to 10 times 2. 20 divided by 4. This is 5 kilonewton. Then you use the summation of F sub y equal to 0. Your B sub y is going to be 10 minus 5 is going to be 10 kilonewton. And then based on the third law of Newton, this 10 kilonewton will be this 10 kilonewton. Okay, this is, no, 5. This is 5. Sorry, this is 5. This is 5. Let me elapse this a little bit. Okay, this is 5 kilonewton, not 10 kilonewton. This is going to be 5 kilonewton, and then B sub y is 5 kilonewton, and this is going to be 5 kilonewton. And then you can analyze this structure to determine the moment M sub C equal to 0. Take the moment here, even though there is the shear over here, the shear V sub C gone. Okay, so you have M sub C equal to 10 kilonewton meter, 5 times 2, and you do the summation of F sub y equal to 0, V sub C equal to 5 kilonewton. So this is the analysis in which you change the statically indeterminate like this into the statically determinate by using the concept of inflection point. Okay, and then you can use what's so-called the free body diagram and equation of equilibrium to solve for this type of structure. Okay, and let's move to another one. Another one, coming to this frame. Most of this frame has the degree of indeterminacy equal to 18. The experienced engineer usually separate the beam into segment, into floor, into beam, into column, into fitting, as I previously explained to you guys. Now, let us consider the pink beam. Okay, it is in the middle of the structure. If this beam connected to the column on the left and to the column on the right, and the column are very strong, very stiff, so we may assume this one as the fixed support. Okay, when this one is the fixed support, you can find this one WL square over 12, this one WL square over 12 for the fixed end moment. And you may have this one WL over 2. Okay, this one WL over 2 at the end shear. Okay, and then you can analyze this structure coming back to the ruler. The beam will defect like this. That is going to have two inflection points occur on the left and occur on the right. By using your ruler, you will get this one concave downward, this one concave downward, and this one gonna concave upward, and the symmetry deformation. I didn't do a good drawing on this. It's going to be symmetry. Okay, and what happened is you can determine the location of this inflection point by just consider only this portion of this beam to set it as the X, and then this is going to be the WL square over 12, and this is going to be the load WL over 2. And also there is the uniformly distributed load act in this X portion, and then this is the inflection point. You may do the summation of the moment equal to 0 here, and you can determine X equal to 0.21 L, 0.21 L, or you may come to check over here this end shear WL over 2 and the end fixed moment WL square over 12 on the left and on the right are equal due to the symmetry of the structure. And you like to determine the inflection point, you just cut it at a point and you set that point to be the X. Okay, and then you may take the moment. Okay, you measure here over here. When you take the moment over here, M here is positive, so you get this equation. Okay, you can do it by yourself, and after solving this, you get the X equal to this number, and then you have one at this location. Okay, this one at this location, and another one you may measure it, and then you get it over here. Okay, and then if you subtract this L by 0.7887 L, you will get this one for 0.2113 L, which they are equal, due to the symmetry of this beam. Okay, and now there are another end of this when the column is very, very flexible. Okay, you can assume this portion as the pin. Okay, and then the inflection point for 0 moment will occur at X equal to 0 and X equal to L. Okay, and in the real world, the column have some stiffness between the case 1 and the case 2. That means the inflection point by using this can be the average between the case number 1 and the case number 2, and let it to be just 0.1 L. Now you may use this structural model for your approximate analysis of the beam in the frame. Okay, and by this one you may check, even though the frame has the fix, and the frame has the pin, the point that has zero moment will be very close if your structure is small, especially only one bay like this, okay, or two bay, or just 2-story. This approximate analysis is not for the whole general thing. As the young engineer, when you graduate and then you take the council of engineering examination, you will get the engineering in training license. Okay, you can analyze and you can design building, but the building can be only 3-story, or you may have 3 plus a half story. Okay, that is going to be about 3 to 3.5 floor, and that is another requirement, the area of the building, of those kind of things. So when we talking about the approximate analysis, our assumption will hold to the building that is going to be small building, low-rise building, and I will concentrate on that portion. For the author, I will let you guys to graduate and work on yourself later based on this knowledge. Okay? Now, coming to the exact result, and I like you guys to take a look, to take a notice of the moment diagram of the frame that's subjected to only the vertical load. You can see this frame has what? Has the degree of indeterminacy of 18. You will analyze this frame by using the approximate analysis. You got to find 18 assumption, and you can see this is the point. That's the frame has the inflection point 6 on the roof and also 6 on the second floor. So the assumption for this will reduce, okay, the 18 degree of indeterminacy by the 16 inflection point. And then compared to this, there is another 6 assumption that require us to make this structure to be analyzable by free body diagram and analyzable by the equation of equilibrium. And since the frame is subjected to only the vertical load, let's say this is vertical load, so the summation of the force in the x direction can be approximate to be 0. So by use the summation of x sub x equal to 0, you got 3 equations in the beam for beam. Let's see, just for the beam, that is 4, 5, and 6. You get 6 more conditions based on axial force in 6 beam equal to 0 due to the gravitational load. Okay, and if you consider the axial force diagram for this frame, you can see most of this one has this the force distribute into the compression on the column. Okay, and then the moment that's called the fractional stress to this structure, to this column, is going to be very small. So we may design the column of this kind of structure as this column subjected to the axial load, okay, such as in the RC design. Okay, just distribute the force like this, okay, into like this into this column, and the force into this one and this one into this column, and you may use the equation. For example, P we use in the design, P may be 0.85 F sub palm C A sub G A cos minus A sub S. This is for the strength of the concrete, plus A sub S times F sub Y. This is going to be the strength of the steel, and there is some kind of strength reduction factor. So you can use this one as the load, and then you can determine A sub S basis on this equation, for example. And then coming into this one, we come to the shear diagram and moment diagram, and again this one confirmed that under the vertical load, the shear force and the moments will produce small stresses in the column. Okay, and you can design the column correctly or properly, approximately, by using this method. And there are some limitations on the approximation. What? The bay. The bay is the length between the column. Okay, supposed to be very close to each other. The difference in the length of the between the column supposed to be less than 20%. And also in the analysis of this, we supposed to have very small deformation, but I enhanced this picture just to show you, enhanced 1,000 times for the clarity of the elastic curve. Okay, usually when you analyze the structure, the deformation going to be very small. Okay, now we come to the next portion. There are some situations in which the frame subjected to not only the vertical load, but also from the wind load and for the earthquake load. Okay, earthquake, EQ, earthquake load. Okay, and most of the frame that we are considered is very large frame. For example, this frame is supporting the elevated highway on the top cockpit. Okay, the weight of the elastic highway is going to be very large. Okay, that is supposed to be very large vertical load. And then in some area, when you decide this, you also need to consider the lateral load that's come from the wind or the earthquake load. So most of the time, this portal frame is the main structure of the building or of the highway structure to resist both vertical and horizontal load and transfer the green load, the brown load to the foundation of the structure safely. Okay, and most of the time this kind of frame has the column with equal length and connected the column with the girder with the rigid joint. So in the model, we will model the portal frame as shown here. Some may be supported by the pin. For example, the portal frame that's used to transport the weight, the high load in the harbor of Thailand. Okay, I have some picture on the chapter 4 of the theory of structure to show you, and I think previous one I also show you that's crane already. And the other one, as I just show you, is the portal frame that has the fixed support, okay, such as the one that supported the elevated highway. And let us consider the frame when subjected to the lateral load. Okay, yeah, let's see this one. This frame has the 1 degree of indeterminacy. Why? Because it's pin. So degree of indeterminacy is going to be 4, And this one can be considered only one free body diagram, so the degree of indeterminacy is going to be 1. When you analyze this, you got to find one assumption to make this frame statically determinate. So how we are going to find the assumption? You got to go to the elastic curve. Okay, elastic curve will show you how the structure deform under the load. For this one, this is the pin can rotate like this. It cannot move on the horizontal or on the vertical. This point must move somewhere over here. Let's say if this one is going to be the delta B, and this one also going to be the delta C. This delta B is going to be equal to delta C because there is no axial deformation of beam and column. Okay, and then the structure will deform approximately like this. You see it's sideways like this. And then due to the stiffness of the beam, this angle must keep at the right angle. Then you got to connect these two portions is going to be downward and then going to curve like this. Okay, and that is going to keep the structure physically correct. Let's say it is correct. That means what? The structure gonna have one inflection point occur at this point, approximately half of the length of the girder. Now we assume that. Not. We assume that for the elastic curve, okay, under the load P, the frame has the inflection point at the midspan of the girder, and we assume this one to be the hinge. And what is going to be the hinge? Summation of the moment here is going to be 0. So we can separate this frame into two free body diagram. And under this, you may write what the unknown. This is going to be 1. Okay, this is going to be 2. This is going to be 3. This is going to be 4, and then 5, and then 5, and then 6, okay, and then the normal force. Okay, so we have N, we have V, we have M, we have A sub X, A sub Y. Okay, we have B sub X, we have B sub Y. And what we can solve for this, you may just take the moment here to be 0. So when the moment here to be 0, the unknown here will be what? Will be A sub X, A sub Y, B sub X, B sub Y, N and V over here. The total of 6. And you have 2 free body diagram. You can solve it by the equation of equilibrium. Okay, I will let you work on this later. And next, from this approximation, the horizontal reaction and shear at the support A and at the support B, A sub X and B sub X, they are equal and act in the same direction. And then you may analyze this frame to determine the result like this. I like you guys to go back and find all the reaction and internal forces in the frame and draw the shear diagram and draw the moment diagram. And also we can confirm the result. If you run this frame that has 3 meter height, 4 meter length of the beam, you can determine the reaction by using the computer program. And you can use the result for your assignment, and then you can check, you get the exact solution for this assumption. And then when you do for the moment diagram, okay, you also can get the same value of moment diagram. Now we move to the frame with the fixed support. Now we have 3 degrees of indeterminacy. That means what? That means we're going to find 3 assumptions. What is going to be 3 assumptions? Draw the elastic curve, and then you can see we have the inflection point that we have studied before from the elastic curve, three of them. One is at the mid length of the beam, another at the mid height of the column, and then you have three inflection points. The point that has moment equal to 0. So you can assume these 3 points as the hinge. Now, you also can determine the end shear here. They are equal as before and act in the same direction. Based upon this, you can use the free body diagram and use the equation of equilibrium, and you determine the reaction, and you determine the internal forces and the forces and moment that occur in the structure. You may draw the shear diagram, you may draw the moment diagram. You got to be able to. Okay, and then you can check the result with what? With the computer program, but this time the result is not that the same as the previous frame. When you compare it, you can see some error occur in this one because it's depend on the structure, it's depend on the support that we use, approximate analysis. And I should mention that usually we use the factor of safety equal to 2.0. That means we have about 200% difference between the error and the exact one. So approximately for the preliminary analysis, you may see there are some error, but that error is not that big compared to the safety factor that we have. And then we also didn't use this one as the end result because we're going to redesign and we're going to reanalyze and redesign the structure later. And anyway, I like you guys to go back even though it has some error, but it's practical. I like to show you this one. Practical. Engineer must be practical, okay, to be able to work. And when you do some practical, don't forget about safety factor. You got to put some safety factor to our work. Next, there is the combination between the pin and between the fixed. And I also like you guys to go back to work on this problem. On this problem, again, you put the hinge at the mid-length of the beam, but you put the hinge only 1/3 of the height of the column, okay, just 1/3, and then you can do the same analysis, get the reaction, get the reaction, get the what, get the shear, get the axial load of the structure, okay. Then come to this PowerPoint. This is very important PowerPoint. I like you guys to remember this moment diagram due to the lateral load. Okay, this is due to the force that apply from the left to the right and have the moment diagram in this way. And if I give you the examination, the wind blow from the left to the right like this, you got to remember this moment diagram. And if I reverse the direction of the horizontal lateral like this, you guys must know that the moment diagram will reverse its direction, but it's going to have the same result. Okay, it's going to have the reverse direction like this. So this is important again. This one is very important, and I will use this moment diagram in the example before the end of this class. And I mentioned about when the direction of the load change, you also be apply this moment diagram to that problem. Now we have 18 degree of indeterminacy. Remember? So how we will analyze this frame? This frame based on the lateral load. Now, since the moment diagram change compared to the vertical load, the inflection point again occur like this. We have 6 plus the inflection point at the middle of the column. We have the total of what? Of 14 inflection point, which is less than the 18 that we require. So where another flow come from? This is going to produce 2 methods. One is going to call the portal method. Another one will going to call the cantilever method. Okay, in the analysis of this frame subjected to lateral load, there are 2 methods, and I will very concentrated on this portal method because this portal method is good for low-rise building. And then, as I show you, the young engineer most of the time work with the low-rise building. Again, what is the portal method? Okay, 4 more conditions. Based on the compression method, they just assume that, okay, under the lateral load that act on the structure, the shear force that occur in the beam at a given level, they are equal. Okay, the shear force for the beam in one story, they are equal. Okay, and what happened when the shear is equal? The axial force due to the lateral load in the column, in the interior column, they are gonna have 0 forces. If that occur, you got 4 more assumptions. Okay, but for the cantilever method, okay, the textbook said this one good for the high-rise building. In this one, the assumption said the axial force that occur in the column will be distributed based upon the length that's measured from the centroid of the column cross section. Okay, let me put this one. That means the force here will have some value which is less than the force over here because this one is farther than this one. Okay, that means all the column, this one will have large axial force, this one smaller, this one smaller, this one is larger. This is very good approximation compared to the portal method, right? Yes, it's good, but it is not quite neat for the low-rise building. Okay. Second, it is harder to do the computation. So I usually not design my examination based on cantilever method. I usually has my examination based on the portal method. In order you guys will have a chance to measure your skill as the young engineer. You're supposed to be able to show this one clearly. Okay. Now again show you the elastic curve and then confirm you the inflection point that occur in the middle of the girder and also approximately at the middle of the column, and you get 14 assumption and you need 4 more for this string. And for the exact solution, this one confirm you about the portal method. Let's assume the shear force in the beam at the same story are equal. What I mean, they assume this one equal. That is a little bit different. If you have one story, this is very correct. Okay, but it may have some big difference if you have 2 or 3 stories, but as an engineer, you never work larger than 3-story building. Okay, that is going to produce 4 additional conditions. And for the Cantilever method, the axial force in the column on the same story are proportional to the distance, okay, from the column. That means the distance from the centroid of the total area of the column and the distribution of the force on the edge will be larger than the interior column. And I will be talking about this later. Next, come to the portal task. In some cases, we didn't use the girder. Okay, we didn't use the girder to link between the column. When the span of the structure is very large, truss is more efficient to use than the girder. That's why some building has the truss to link the column, and then we call this as the portal truss. And there are some examples that's used for the portal truss, such as in the hangar, like this one. Okay, that's used to keep the airplane out of the vehicle, such as out of the snow, out of the high wind. Okay, in the analysis of this, you may assume, okay, the hinge occur about half of the length of the column, and the length of the column measure from this portion to the bottom. And then if the pin are used to be the support of the portal truss, okay, you may assume the horizontal reaction are equal and act in the same direction. If you use the fixed support for this one, okay, you may add more assumption than the pin support portal truss by assuming the inflection point at this portion. Okay, and then come to the ACI coefficient. ACI coefficient giving you the guideline to estimate the moment that occur in the beam of the frame. If the exterior support, okay, has no resistance for the rotation, or you may have just the beam that's put on the wall, okay, not very not cast together, just beam that's put on the wall, okay. The moment that you can estimate at the middle can be WL square over 12. However, if you be connected to the edge of the building, the maximum positive moment is WL square over 14. Okay. If your beam is in the interior of the building, it's going to be WL square over 16. And if you compare them, you can see that this one will provide the largest moment, since the coefficient is going to be the largest one compared to the second and compared to the third. Okay, so you must be very careful. You must classify your beam before you select the moment coefficient from the ACI code. Okay, and that is very thing of this. For the negative moment, okay, you may use for each cases, and we may notice that the largest one is going to be WL square over 9, which is a little bit less than the largest moment occur in the simple beam, which is WL square over 8. Okay, and now let me move a little bit to the portal frame, okay, for the frame with the lateral load. And before here, I put some important point to you guys on the moment coefficient for the continuous beam, for the beam in the frame, and that is based on the design code. Okay, it's not from the building code. It's going to be the technical thing, and it's only used for the American concrete in situ. Okay, and it's adopted by the EIT of Thailand. The portal frame, in the low-rise building like this, you can see a lot of this building in the earthquake-prone area, such as one in the California, because this frame is very rigid frame, and it can take a lot of large earthquake force. Okay, but how to analyze this one? Okay, it depends on number of bay. This one, 1, 2, 3, 4, 5, 6, 7 bay. This is going to have the degree of indeterminacy. Pretty big. 1, 2, 3, 4, 5, 6. Okay, the model of this frame will look something like this. And if you like to determine the degree of indeterminacy, how many components? Okay, that is going to be 1, 2, 3, 4, 5, 6, 7. It's going to be 7 times 3 minus 3 times 1. Okay, that is going to be 21 minus 3. This is going to be 18 degree of indeterminacy, even though there is only one story. Let's make it a little bit more simple. I won't make this kind of frame as my examination. This is too big, okay, to be the examination problem. Most of the time I may put just 2 or 3 bay. If we consider this portal frame for 2 bay, the degree of indeterminacy of this one going to be 6. That means we require 6 conditions. And if you consider the elastic curve of this frame, you may see 5 of them. So you may require 1 more. Okay, this is only 5. You may require 1 more to set this frame to be the statically determinate. What is this? It depends on the structure. No, it depends on the method you use. One is the portal, one is the cantilever, and this kind of low-rise building, the portal going to be easier. Just set the shear force on the roof floor is the constant, and when set the shear is the constant, this column will take no axial force due to the applied load. Only this one, okay, and this one will take the force. And then based upon this, you also have the assumption about the shear force in the beam on the same story are equal. And then this assumption make the axial load for the inside column is 0. Put one more condition. And this show you the portal method. Okay, to assume again the shear force going to be constant and the force inside interior column, they are 0. And then moment diagram for this again, please remember it. And we will use this as a guideline in the analysis of this frame. Okay, for the portal method, we require 4 more, in which the force in the interior column are 0. And then I take a note on this. You got to stop the video and read it carefully. And then I also mentioned about when the load, just check the direction, how you guys gonna analyze this structure. It may be checked like this too, or it may be checked like this too. Okay? Now, to the portal method, please listen to me carefully. This 18 degree of indeterminacy structure will be analyzed by using the portal method. So we have 14 inflection points like here, and we require 4 more conditions, which are the interior column has the 0 force. If you assume that if you cut the frame based upon this line, there is no internal force in these two columns. Again, if you cut it into this line, there is no internal axial force in these two columns, and then you can analyze this structure based on this free body diagram easily. So when you cut the frame to the inflection point, okay, consider only the roof form, okay, the height change to half, and then if you take the moment here, you can find the axial force here. When you get this axial force, you use the summation of vertical force equal to 0. You get this light blue. Okay, just take this one, and then you get 1.6. When you get 1.6, summation x of y equal to 0, you get this one 1.6. And based upon this again, okay, we're going to determine the shear that's occur over here. Now we just cut the frame. Consider here, and later we will find shear here. Okay, let me go to the first form first. Do the same thing. Take the moment over here. You get the force here. Summation of f sub y equal to 0. You get the force in this point. Okay, it's 11.6. Now just consider only this portion. When you cut this portion, when you cut, we will have the moment, we will have the shear, we will have the normal force. So the free body diagram gonna be something like this. Okay, the force that we are considered is this one. Summation of f sub y equal to 0. Downward is positive. V sub a to downward plus 1.6 is going to be 0. So what we have, V sub A2 is minus 1.6 equal to kilonewton. So the direction of this is wrong. It's going to be in the reverse direction. Okay, it's going to be in the reverse direction. So this direction is wrong. The reverse direction is going to be upward to make the force over here in balance. And then when you consider the portion of the beam that connect to this point, okay, the upward force here going to be the downwards. And when this one is downward, and then the shear across here going to be constant. So the shear diagram going to be minus 1.6. And then it's going to be constant with slope equal to 0 because W here is 0, dV by dx is 0. And then this one for sure is going to go upward and close it. Okay? And now you must remember what I asked you guys to remember is going to be the moment diagram. And the moment diagram of this one will be in the form of this, in the sawtooth, okay? Funley is a sawtooth, in the sawtooth like this, due to this kind of applied. And then come to the equation to determine the moment. Moment at B minus moment at A equal to the area of shear diagram between A and B, between A and B. So if this one is the B, okay, let's say this one is the B, the shear here is 0. If this one as the A is going to be 0 minus M sub A at B over here is 0, and then it's going to be equal to the area here. The area here is minus 1.6 times half of this times 2.4. So you will get M sub A equal to something kilonewton meter minus cut out. You got this one to be the positive value. And when you get this, how much? This is going to be the same value, but this one going to be in the negative. Okay. And then based on this, I can determine the moment here equal to the area here. Okay, this is going to be minus 1.6 times times 7.2 divided by 2. And I also can determine this one. This one will be 3 meter. It's going to be minus 1.6 times 3.0. And this one going to be the negative, same value. And this one also be the negative with the same value. Okay, we will get this one based upon this one. The moment at here is 0. Okay, we find the moment at A. The moment at A will be equal to this one is going to be the area over here. Okay, and negative, you cut negative, you got this one 3.84, and then this one gonna be minus 3.84. This one is plus 5.76. This one is minus. This one is plus 4.8. This one is minus 4.8. So it's not really easy, right? It's really easy. It's going to follow this one. Just compute the area that's shown here. Okay, that's shown here for this one, and the area that shown here for this one, and and the area that's shown over here for this one. And then come to the moment diagram. When you draw the moment diagram, you got to provide me the slope, and you can see all the slope are equal to minus 1.6. And then come to the next one. Now we consider the orange dash one. Okay, and then this 1.6 will be provide the upward force, and this 11.6 will provide the downward force, and we require to determine the shear over here. Okay, you may consider only the vertical force, even though this one has the 40 kilonewton. We use the summation of F sub y equal to 0. Okay, and based upon this, it's going to be V sub A1, and downward is positive. So we have V sub A1. Okay, plus 11.6 equal to 1.6. So V sub A1 is going to be minus 10 kilonewton. So what we have is going to be this upward. See, it's minus 10. You change this one to upward, and then this 10 kilonewton will change to this shear force of 10 kilonewton, and then all the shear force are equal. You may draw the shear diagram based on this. It has equal minus 10 with the slope equal to 0. And then we can draw the moment diagram where 24 come from. 24 come from this area. This area is half of this. Okay, and then where 36 come from is going to be 10 times 7.2 divided by half. And where 30 come from, 30 come from the same thing, the area over here. That is very simple. And if you can remember the shape of the moment diagram, you also can draw the slope to be minus 10 along the way of it. Okay, that's going to be very easy. Now you get the shear and the moment for the beam. Now we come to the shear and the moment of the column. And I'd like you to follow the sign convention of the engineering static. This one positive 3.684. That's follow this one. So direction is supposed to be this. This one is negative, so it's going to be like this. Okay, you understand the sign convention, right? So you can draw like this, and then you got to transfer the moment to the column. And at this point, 3.84 at over here, and it's going to be resisted by this one, and this one will be by the third law of Newton. You get this one. Okay, and then if you follow what we have for the moment diagram of of the exact analysis. You will see the moment at this end and the top gonna be the same. Okay, and then how 9.6 come from? Just combination of this. How 10.56 come from? Combination of this. And 4.8 come into this. And when you get this one, you know this from the moment diagram, all the answer is going to be very easy to solve for. Okay, and now we come to the second form, and we can determine the shear. Okay, you can determine the shear at the end. When you get this this green shear, you will also get this purple shear also. Just take the moment of one column and then you will get this end shear, and the top shear will be the same. Okay, and again it will provide you with the shear diagram with the shape like this, and it will provide you with the moment diagram with the shape like this. Okay, this will guide you, and this is going to be 3.84. However, this one elast, this one gonna be to be this one. Okay, this one is negative, this one negative, this one gonna be positive, and slope here is going to be plus equal to 2.1 over here. Okay, let you guys work on this by your own, and then you will get for the first form. On the first form, again, you got to take the result from the previous one. Okay, you take the moment here from the previous one, and then you got this 24 that you have, and then it's very simple where this one come from. Just take 24 minus 3.84. Okay, and if you interested in this point, you may also can use everything and draw this one. This one is 24. This one is 9.6. This one is 36. And finally, you can determine this one by summation of the moment at this joint to be 0. And then you get this 50.54. And then you do the same thing, same consideration, you get the end shear. Okay, and from this is going to provide you the reaction. This one come from very first step. Okay, axial force that we take from the moment, and then the shear 7.4, 7, 18, 0.6, 7, 20.53, and 9.3. And then the moment 20.16, and then 15.40, something like this. This is for what? The reaction. You use this reaction to decide the foundation of the building. Okay, you may use the reaction to decide the foundation. And then for the shear and moment, for the beam, you have this already. For the column, you may draw it like this. So that is the end of very first example on the analysis of the frame by using the Cantilever method. There is another one that is analyze the frame by using the Cantilever method. This method, again, the textbook said is good for the high-rise building, but usually when you analyze building nowadays, you may use the computer. That is going to be easier. The assumption of this bases up on the fact of the cantilever beam in which the fractional stress of this beam linearly distributed with respect from the distance from the neutral axis of the beam. In this one, we use the centroid of the area of the column in the frame as the neutral axis. And then the axial force will be distributed based on the length that you measure from the centroid. The larger length, the larger load, the smaller length, the smaller load. And then what we have is the distribution of the force will be different like that. And based on this approximation analysis, the inflection point of this frame still the same. There are 5 of them, and there is one more assumption based on the portal method is this one. Okay, you may stop the clip and lead it. The magnitude of the axial force in the interior column will proportional to the distance from the column. Okay, that's you measure how much from the distance from the centroid of the section. And then the shear on the same level will be different. Unlike the previous one, portal method, all the shear are the same. But anyway, the moment diagram will be the same. Okay, no matter if portal method or no matter if cantilever method, you got to remember this triangular shape of the end moment and end shear. And again, in the cantilever method, it is your duty first to determine the total area of the column and then determine the centroid of the area of the column. Why? Because the axial force in the column will be distributed, the magnitude will be based on how far away from that point. Okay, when the close one is small, when it's larger one, the axial load, axial force is going to be larger. Now, just do the same as you study from the engineering static, and then you get the result. Okay, and by doing this, there is no direct connection, but you got to use the slope. Slope here is the K2. Okay, based on the slope, you can determine the size of the axial force due to the slope and due to the length. Okay, you know this one, right? For example, if you have the slope for K2, and this is going to be R sub A2, and then this is the distance that's measured from this one to this one. Okay, this is going to be 8.7 meter. So this is 8.7. So R sub A2 divided by 8.7 is going to be K2. And then R sub A2 is going to be K2 times 8.7. Okay, 8.7. And this one is 9.3. So it's K2 times 9.3. So the unknown is going to be the slope K2. Okay, this is 3.3 K2. This is 3.9 K2. And you take a moment, okay, at that same point by using the force that's based on the slope, and then you get the K2. When you get the K2, you will get the axial forces in the column that's distributed from the centroid of the column of the frame. Okay, farther get larger, closer get smaller, and then you do the same thing for the column on the first floor. You find the K1, and then when you get the K1, you get the axial force in the column. And you can see by doing this, the calculation require a lot, right? Okay, and since it didn't use much for the tall, the two or three story building as the young engineer can work. So this one we didn't much focus on. And for the shear and for the moment, diagram of the beam, you do the same, but it will require a lot of computation to do so. Okay, but the idea of the drawing of the shear diagram and moment diagram are the same. Okay, and then you just follow what we have over here. You will get the shear force for the, this is for the floor, the orange floor here, and the computation require a lot of things because the shear on one level, they are not the same. And then after you get the shear diagram, you get the moment diagram for the area, as we did before. Okay, if you understand the portal method, you will do the Cantilever method easier. Okay, after you get the shear diagram and moment diagram of the beam, you do the same thing for the shear diagram and the moment diagram for the column. But you got to be very careful in the calculation. I like you guys to go back and compare the reaction for this same frame, for this same problem, by using the portal method, by using the Cantilever method, and you can see the results are a little bit different, but not that much. And you're supposed to be aware of this approximate analysis that can be only used for the preliminary analysis and design of the frame. Okay, that's all I have for today, and I hope you guys will focus on the frame with the vertical load, and for the frame with the lateral load. For the frame with the lateral load, focus on the portal method. There are two problems in the examination for this chapter 5, frame with vertical load, frame with lateral load, and there are some examples that I already show you guys in the extra example over here. I like you guys to go back and try to work by your own on this example. This both subjected to the vertical and lateral in the same problem. Okay, and I also planning to design another one that is subjected to only the lateral, and I can change this one, take this lateral force out, and then put the vertical force to this problem. Okay, that's all I have for today.